Good afternoon, everybody. My name is Mona Behl, and I serve as Associate Director of Georgia Sea Grant at the University of Georgia. I'm also a non-residential policy fellow with the American Meteorological Society. With me today, we have Dr. John Nielsen-Gammon from Texas A&M. John, would you quickly like to introduce yourself?
Had to hit the right buttons. Yeah, sorry. Yeah, hi, I'm John Nielsen-Gammon. I'm at Texas A&M. I'm the Texas State climatologist and outgoing co-chair of the Predictability, Predictions, and Applications Interface panel for U.S. CLIVAR.
Fabulous. Thank you, John. We also have Dr. Charles Manski, who is our first speaker. He is the Board of Trustees Professor in Economics from Northwestern University. We also have Dr. Derek Lemoine, who is the Associate Professor of Economics at University of Arizona. Dr. Raphael Calel, who is the Assistant Professor at Georgetown University and London School of Economics. Dr. Kristie Ebi, who is the Professor in Global Health at the University of Washington. And Dr. Nathalie Voisin, who is the Chief Scientist for Regional Water Energy Dynamics at the Pacific Northwest National Laboratory and the University of Washington. Each of these experts have contributed articles to this winter edition of Variations. So let me, and you can read the titles for their different articles that are published in this issue of Variations. Before we hear more from them, I just wanted to provide a brief overview of what this Variation edition is all about and how it came to being. So in 2020, during the PPAI meeting of the US CLIVAR Summit, we had a session that focused on long-term climate prediction. And in particular, during that session, we hosted a panel discussion that explored the connection between GCMs, global climate models, and integrated assessment models, or IAMs. That are considered for the quantification and propagation of uncertainty through such models. And we also discussed during that session ways in which climate scientists can contribute to the value of integrated assessment models and their interpretation. Through our deliberations, after listening to those experts, it was quite clear that experts who work in the field of climate change, we approach climate change from different disciplines, different perspectives, and very often we talk different languages. We, let alone working with each other or understanding the value of doing so, we're not even go past the language barrier. So we were inspired after that session to put together this issue of Variations that is an attempt to address some of these challenges that experts from the disciplines of physical and climate science, economics, and health experience. So as you will hear from the different experts and speakers that we have today, there are opportunities for us as climate scientists to improve the value of climate data and models by truly understanding ways in which our data and models are conceptualized and put to use by other disciplines. So this is an opportunity to do so. Before I invite our first speaker, Dr. Charles Manski, to provide his comments, I really wanted to express our deepest gratitude to Jenny and Mike at US CLIVAR for giving us the opportunity to put this edition together, and most importantly for their incredible support and coordination in making this effort happen. So without further ado, thanks to all the authors of this edition of Variations. We learned a lot, and hopefully the process was beneficial to you as well. But we look forward to hearing more from you. John, is there anything else to add before we begin?
I don't think so. I'll be managing the Q&A after each talk, and also, assuming we have time at the end, we might have just a broad panel discussion, and people have more general questions for everybody.
Fabulous. Thank you so much, John. So as John mentioned, John would be moderating the discussion. And as you listen to the speakers, please feel free to jot down any questions that we can ask them towards the end. So without further ado, let's invite Dr. Charles Manski to talk about addressing deep uncertainty in policy analysis. Dr. Manski, please take it away.
Thank you very much. Mona's introduction, I think, makes me feel comfortable for being here. I'm an economist and not in these interdisciplinary situations in terms of dealing with language, and so they can be sometimes difficult. I think it's great that Clivar is doing this. Let me apologize at first that I made a mistake on my first slide and I wrote Clivar exchanges rather than Clivar variations. I hope that's the only mistake in the slides. So this work is addressing deep uncertainty in climate policy analysis. My co-authors are both on the webinar. Alan Sanstedt is an energy policy analyst at Lawrence Berkeley Labs, although this work does not fall within his LBL responsibilities. So in the published Clivar piece, his LBL affiliation doesn't show up there. Steve DeCanio is emeritus professor of economics from UC Santa Barbara. And as Mona said, I'm at Northwestern University. The work that we're talking about originated in an article in PNAS that Alan and Stephen and I published last spring. And they saw it in PNAS and asked us to participate in the Clivar issue, for which we're grateful. The title is Addressing Partial Identification in Climate Modeling and Policy Analysis, and there's the URL for the PNAS article. Now, there's only a short amount of time, so I'm going to summarize and then go through it, and then tell you about a little bit of work in progress at the very end, if I have time. So, of course, climate models enable policymakers to analyze the consequences of societal decisions about energy production and use. Even though there's been a huge and very impressive amount of work in developing climate models and also integrated assessment models, the complexity of the climate system is great, and so we still have an imperfect understanding of some components, and that generates a deep uncertainty, which we'll talk about in a minute in terms of what that means. I think probably many of you understand that term. A consequence of this is that there's no consensus model. There is no agreement on what the right model for making projections of the climate are. So there's multiple models in use. And when you have these multiple models in use, there's been a need to aggregate their forecast. And the traditional way of doing that has been by doing model weighting of one kind or another. We actually argue against model weighting, and I'll explain why. The alternative that we pose in our work comes from econometrics, a field that I work in, on what's called partial identification analysis. And then we apply decision theory using minimax regret analysis. And we think that this approach offers a reasonable way to deal with uncertainty in climate modeling. Now, I don't think I need to spend more than 1 second to tell people on this webinar all the difficulties and complexities in modeling the climate. There may be at some abstract level agreement on the basic physical processes, but when you get into the details of climate modeling, there is no consensus on exactly how to model things. There are numerous practical choices in computational climate modeling. And there's some parts of the basic physics. I'm not a physicist, but I've learned that some parts of the basic physics, like cloud formation and heat transfer, are still not yet fully understood and must be approximated. So there are multiple climate models that have been developed and are in use. And there is no consensus model, and there's no single accepted quantitative climate projections that can be specified with current knowledge. Well, so climate scientists have known this for a long time. And so what's evolved is to do what's called multi-model ensemble, or MME analysis. And so you have multiple models, they make multiple forecasts, and the standard approach has been to combine the multiple forecasts into single projections of future greenhouse gas emissions, of course, as a function of scenarios for abatement and so on. And the perception has been that modelers aggregate these multiple forecasts into single projections because they think that policymakers have to have some single projection for decision making. Now, although that's been done for a long time, climate researchers are very well aware that there are persistent problems in combining model projections. Typically, what's done is by taking some kind of an average of the projections. There's often it's a simple average. Some people talk about model democracy, and but there's no good reason for it to be a simple average, and so it's natural for modelers to think about taking weighted averages and think about giving higher weights to models that are more credible in some sense. But that hasn't, I have to say, I don't think that's worked out that great. There isn't really consensus on which models are more accurate than others, because even if you look at the historical performance of models, what we need is to use the models to forecast the future, and so their historical accuracy need not be the same as how well they're going to forecast into the future. Okay, so that's the background that I'm sure most of you are familiar with. So what do we do? What we do rests on a concept from econometrics. It's called partial identification. And although the concept developed in econometrics, it's 100% just as applicable to physical science modeling. What partial identification means is dealing with situations in which the underlying mechanisms, dynamics, or laws governing a system are not completely known and cannot be credibly modeled definitively. So you may have multiple models, all of which have some level of credibility, and you're just not sure which one's right. Now, what partial identification generates in terms of uncertainty is, and I have various names used in different disciplines here, ambiguity, model uncertainty, deep uncertainty, or epistemic uncertainty. If you go across disciplines, all of these words, terms are used. They basically all refer to situations in which you don't feel comfortable placing, dealing with uncertainty in a fully probabilistic way, just putting different probabilities on the truth. You just have to entertain various possibilities. And it's our view that deep uncertainty well characterizes the present state of climate modeling, that it won't be sufficient to take what might be a classical Bayesian view of putting probabilities on different models and then operating with them, but you really have to deal with them as separate models. Well, if you have a set of separate models and each one may have some credibility and you don't know which one's right, then the idea of averaging across predictions doesn't really have a lot of logic to it. What goes on in partial identification analysis is rather to deal directly with a set of predictions that's yielded by different models, by multi-model ensembles in the case of climate models. And so then the question is, well, let's think about this from a policy perspective. If we have a set of predictions made by a set of models, then how are we going to use that for making policy? And there are classical answers to this in decision theory literature, and two that we focus on, one of them which I expect is very well known and the other maybe not, is minimax and minimax regret decision rules. Minimax is a very, very long history. It's preparing for the worst case and then acting as if the worst case is going to happen and going with that. And it really, minimax ideas get embodied in the precautionary principle for dealing with climate change. But we actually don't use minimax in our analysis. We use the minimax regret rule because we think it deals with uncertainty in a more nuanced way and a less conservative way than minimax does. And so for those of you who aren't familiar with minimax regret, try to explain it simply. Suppose that a policymaker selects one model from an ensemble and chooses an optimal abatement path, assuming that that model is correct. And when I say an optimal abatement path, it means that you've had some measure of social welfare and you've tried to optimize that, as the integrated assessment literature does. Now, the problem, of course, is that the model that's been assumed in optimizing may not be correct. And so regret is the term in English that's used, and it's, there's a whole mathematics, formal mathematics behind this, for the loss in welfare that will be experienced if the chosen model is not correct, and therefore the chosen abatement path is actually suboptimal. You're acting as if it's optimal, but it's really not, and so you get it wrong, and there's some loss in welfare, and that's called regret. Now, you don't know which is the right model, so you can't just minimize regret, which would be a great thing to do, but it's not feasible. So what the MMR rule does is it chooses a policy that minimizes the maximum regret or the largest degree of suboptimality across all climate models deemed possible. The minimax regret idea, as I say, is a classical idea. It goes back to about 1950 in the decision theory literature, and it's used in many areas of research. I could talk for hours and weeks about it, and we'd be happy to get email from anybody who wants to learn more. So what applying the MMR rule does is enables nearly optimal decision to be made regarding abatement without requiring single projections to be made by averaging across models. Now, that's a general idea, general framework. What we do in the PNAS article, after setting it out abstractly in mathematical terms, is we wanted to give a computational example. So we developed a pretty simplified integrated assessment model, which has three key elements, which are really common to lots of IAMs. And the first is the climate modeling. It's number one up here. Those are the equations coupling greenhouse gas emissions and abatement to the accumulation of greenhouse gases and the resulting temperature increases. That's the climate modeling. The other two, numbers 2 and 3, the damage function and the abatement cost function, that's where the economics comes in. The damage function is the quantification of the effects on the economy and maybe on society more broadly of climate change. And the abatement cost function, of course, is that it's costly to perform abatement and get the gases out of the atmosphere. We follow the tradition in the economics literature on integrated assessment of modeling costs and damages, reductions in gross world product. The objective is to minimize the cost of abatement and damages over a time horizon. There's a long, dynamic optimal control literature that's evolved for doing this, and I'm sure some of you are aware of pieces of this. On the climate modeling side, for the uncertainty, we wanted to get this very simple. So we really wanted to characterize different climate models by a single parameter. And the way we do that is following the work of Matthews et al. In Nature in 2009, and which is a very, very nice summarization of a long-term relationship between aggregate carbon emissions and global mean temperature. And that they, as an the assertion in the Matthews et al. Paper is that the ratio of temperature increase to cumulative emissions, which is called the carbon climate response, is roughly constant over long periods. So we get models. We actually get 6 models. We take 6 very prominent climate models. We characterize the differences between each of these climate models by the differences in their CCR. It's their what's embedded in the models as to how sensitive global temperature is to greenhouse gas emissions. And so we have these 6 models, and we don't know which one's right. Well, you don't know which one's right, then we can imagine that different policies which would optimize, assuming that each model is correct. Of course, that may not be correct, the right thing to do, but you might optimize assuming each model is correct and then see what happens, and that results in 6 different solutions to the abatement versus damage trade-off problem. So then the bottom line in our paper, and this is basically what I'll end with, except for one postscript, is to do to put out some numbers, which we do not view in this paper as in any sense realistic, definitive numbers for use in climate policy. It was rather to give a simple computational exercise so that people would understand the basic idea. So if you look at this table, across the columns, we have a model used for policy. So we have 6 different models, and so you could choose optimal climate policy, assuming that each of these 6 models is correct. But if you look down the rows, I scan down here, well, those models may not be correct. So imagine that I take the policy 1 and I optimize with that. Well, if the correct model is model 1, then I'm going to have 0 regret, because that's going to be the best thing possible. So there's not going to be any loss. On the other hand, if one of the other models, 2, 3, 4, 5, 6, is actually the correct climate model, then choosing model 1 for optimization for policy formation was not right, so there will be positive regrets. And the maximum regret for that is going to be 0.06558. That's the fraction of world GDP that's lost by making policy in that way. It turns out with these numbers, if you look at the bold here, it turns out that, and I say this is just an illustrative exercise, don't take it too seriously, is Model 3. Model 3, if optimizing with Model 3, if Model 3 is really the correct model, of course, that's the best thing to do. Otherwise, you have regrets. Turns out the maximum regret here is when Model 6 is correct, and that's why we get the 0.02071. Now, given the shortness of time, that's all I'm going to have time to say about this, but I want to whet your appetite, if I can take one more minute, with what I'll call a sneak preview. When Alan and Steve and I began this work, we knew that the PNAS article was not going to solve anything. We wrote it to try to open up a way of thinking about making climate policy under uncertainty using minimax regret. And I hope we've succeeded there. But we focus just on climate modeling uncertainty. We say nothing at all about all the economic uncertainties, which is particularly strange for us because we come from economics backgrounds. So we have a new paper, which is not posted yet, but which I think will be posted within the next couple of days. It's essentially complete. And here we add a different dimension of uncertainty, and that is how to do intergenerational discounting. And for those of you who know the integrated assessment literature, you may know that choosing the right discount rate for how to evaluate intergenerational consequences of climate change has been a hugely controversial question. And it leads substantively to very different recommendations for climate policy. So we deal with both uncertainty and also with disagreement about discounting, and then we embed that in this minimax regret framework. Okay, so I hope I haven't gone too far over, and I will stop here.
That was fantastic. Thank you, Dr. Manski. John, you were about to say something?
Yeah, sure. Just a reminder, you can raise your hand for asking questions or put a question in the chat box. And if nobody does that, all you get are my questions. And I have a couple of quick ones. First off, the examples you've given are dealing with basically global scale climate policy. Does the same ideas work if you're working on a local problem?
Yes, absolutely. The basic idea of minimax regret and decision making is dealing with deep uncertainty, uncertainty that you don't want to characterize as a stochastic or probabilistic process at any level. It could be at very localized problems or the global level. It can be oceanographic aspects, atmospheric aspects, whatever. This is very, very broad. I mean, I published papers applying minimax regret to vaccination policy, for example, or criminal justice policy. This is very broad across many, many disciplines. And part of what we're trying to do was to bring it to the attention of climate science. There has been a little bit of previous minimax regret work in the climate literature, and we referenced that in our PNAS article, but we think it hasn't been known the way it should be.
Thank you. And I have one other quick question. One concern might be from a climate modeling perspective, there are certain models that even though we don't know which ones are right, we don't believe some as well as others. For example, the high climate sensitivity models that came out with CMIP6. So this emphasizes, I suppose, what the outlier models do. Is that a potential issue?
The way we did it's kind of agnostic. It doesn't rank one model above another. There are intermediate approaches that are in between classical Bayesian and minimax regret, which would allow you to do something partially of that. I don't know, Alan, you're the energy policy analyst. Do you want to add something on that?
Very quickly, what we used was the CMIP5 ensemble runs generated by the emissions-driven Earth system model. CMIP5, for those who don't, the acronym Climate Model Intercomparison Project. That's one of the studies that does this multi-model ensemble analysis. So the paper, we followed a long history of literature in climate modeling about problems with model weighting and model democracy. And as we say in the paper, despite an enormous amount of work, there's still no agreed way of doing that. So outlying models, you know, the point is that if you can't definitively assign a weight to a set of models, then you need to take account of the whole range, and that's what we're doing. You know, more recently in the AR6 work, they've gotten some much more complicated ways of combining model projections. So we may be looking at that in the future.
Okay, and Raphael, I see you have your hand up.
Yes, thank you for that presentation. I was wondering, speaking of the sort of CMIP 5 and 6, my understanding, and this goes to the minimax regret criteria, my understanding is that generally speaking, climate model ensembles are not constructed in a way to sort of explore the space of possibilities. They are sort of, each of them is trying to come up with a best guess for what's going to happen. So I'm wondering, minimax regret sounds to me like a strategy that makes sense, as Alan was saying. It makes a lot of sense when you sort of have the whole range of, like, when you're deliberately trying to explore the range. But when you're not trying to do that in the first place, does the strategy apply?
Well, it's a limited, the actual computational work that we did assumes that one of these 6 models is the right model. But of course, we don't have any reason to believe that. There could be hundreds, thousands of different climate models that one could construct, and one could do minimax regret over a much larger description of uncertainty than we do here. In application of the method, you're going to have to be practical, you're going to have to take some stand on what's inside the envelope. You know, which models are feasible and which are just crazy and you're not going to consider. So in this paper, we've got 6 because it's illustrated. In the new paper, where we have both, we use the same 6 climate models, but we also now have different discount rates to use. We wind up having a 2-dimensional thing with 42 different possibilities of both models and discount rates. You could go further, and this is why Steve and Alan and I have an infinite horizon research program for ourselves of adding more and more dimensions of uncertainty, like what's the right baseline for abatement, and so on and on and on. So, you know, once you start thinking seriously about uncertainty, then you can think of all kinds of things to add to the uncertainty, but then you know, you run into pragmatic problems that we can't model everything at once, and you have to cut the system down, as anyone who does applied science knows. And so in principle, the minimax regret can apply, you know, to any size, you know, dimensionality of the model space and so on. What we're taking here is a start, and but I think it applies equally well whether it's small dimensional or high dimensional in principle. I don't know if either Steve or Alan, if you want to.
That's an excellent question. So I want to go back to the way you posed your question. The aim is not to necessarily explore the space of climate models. The aim is to make sure that all the available information is taken account of in decision making, right? And so as you're quite right. I mean, it's known that climate models are their ensembles of convenience in general, and they're working on that, these ensembles, but they are not necessarily designed to span the entire space. And at the same time, there's increasing concern in the policy and science community about what they, in the probabilistic sense, call low probability, high consequence events, right? And so what we're doing is, you might say, a certain way, is analogous to that. You know, we're not assigning probabilities at all, but in order to take account of the full range of possibility, this technique has a lot to say, recommend it, because you can take account of all the range of uncertainty in decision making without having to figure out how to do the weighting on the tails.
Yeah, thank you both very much.
It's computationally intensive. It in the paper that Chuck presented, there's a matrix of 36 regrets. Adding 7 discount rate possibilities increases that to over 1,800 possible regrets. So it goes up very fast. Adding just a few, adding uncertainties in the damage and abatement function can go up to 180,000 possible regrets, which we haven't done yet, but that's just an indication of how computational and intensive it is. But it really, by taking account of these possibilities of extreme outcomes, it's really important that the decision process include that, because that's where the action is.
Right. Well, thank you so much for that rich discussion. I think in the spirit of moving things forward, we'll move to the next speaker, and we'll come back if there are more questions to the panel. So our next speaker is Dr. Derek Lemoine, who is going to talk about designing climate science to improve climate economics. Derek, please take it away.
Okay, great. Thank you for putting this together, and thank you, Mona and John, for everything, pulling all the whole group together, organizing the issue, and to Jenny for organizing the issue as well, and for this conference. So I'm going to talk a bit about what economists could use from climate science, like what are ways to kind of change the experiments that are running climate science that might make them a little more useful for the bulk of economic modeling. I'd say the most notable and most obvious advance in climate modeling has been the increasing spatial resolution of models, in addition to just including more components of the Earth system. And it's quite a striking improvement over time in the size of the grid cells and in just the complexities that are included in the models. Unfortunately, for the majority, not all, but the majority of economics work on climate change, that dimension of improvement probably hasn't been super useful. Partly because we were, as was mentioned in the previous talk, we're limited in sort of the depth of resolution that we can explore, or even that we should explore, based on just other constraints in our knowledge. And I'll touch on that in a second. So first, a stylized depiction of what at least one benchmark economic application would look like. So this is like a stylized picture of Bill Nordhaus's DICE model. Roughly, for those who haven't seen it, what's happening is that you are baking a pie in every period. You have some capital stock. The more capital you have, the bigger the pie you can bake. And then each period, you're solving an optimization problem. You're choosing how to carve up this pie. Some of the pie you can eat, that's consumption, which goes to utility, just a word for stuff we care about. Some of the pie can go back into reinvesting in more capital, which allows you to bake more pie in later periods. And some of the pie can be spent to get rid of the emissions that were made as a byproduct of baking the pie in the first place. So that's what we call abatement. Abatement and emissions combine to determine carbon dioxide through a very simplified climate module, which determines temperature as well through the same very simplified climate and carbon cycle module. And then temperature feeds back onto output in later periods and reduces the size of the pie available in later periods. So the intuition behind these models is that you can invest in two different ways. You can invest either in terms of increasing your capital stock to get more pie in the future, or you can invest in having more future pie by reducing your emissions today and avoiding warming that's going to shrink the pie right off the bat in the future. So a couple things to point out. One is that what most of the climate models are giving us is that they're improving the link between emissions and later carbon dioxide and later temperature. So that we're needing to couple what those models are doing to an economic framework. So we're coupling a very simplified version of those models to a very simplified economic module, and then often trying to optimize over the pair. And optimization means you have to run them hundreds to thousands to tens of thousands of times, trying to find the right policy combination that's going to maximize total well-being. So you need to be able to have simplified models that don't obscure the insight you're trying to obtain from the model, while also being light enough that you can actually simulate over them a whole ton of times. So a few things to note about this framework is, one, that it's often used for insight as much as for precise numbers. I would argue that's probably the better way to use them, that using them for precise numbers is a little bit of misplaced concreteness. And part of the reason is that we just know so little about the link between temperature and output. The models are stylized on their own as representations of the climate system and as representations of the economy. But even if they were more detailed, we just don't know what temperature is going to matter for output and well-being in the future. And the whole reason we reduce emissions in the models is because of that link. And so this really fundamental piece is just something we may not even be able to know until after the fact. So improving the representation of the climate models by some decimal points, it's just washing out in the noise of the basic uncertainty and the economic linkage behind that connects warming to the economy. So there's also a limit just in how far it matters pushing on some fronts when other fronts are just so noisy. So what I'm going to advocate for is that what we could use in the climate science community is simple modeling frameworks that can capture big picture phenomena that actually might drive things beyond the level of decimal points. So I think refining the projection of warming from, let's say, doubling CO2 to 3 to versus 3.2 degrees is just not going to matter that much. But there are lots of other things that actually will matter quite a bit. And that's what I'll try to touch on. In particular, kind of the high-level overview is I want to emphasize the development of simple mathematical frameworks that properly account for uncertainty and that can capture the central stories from more complex models. We don't want to get the basic story wrong. We also want to be able to generate other likely outcomes from the same simple mathematical frameworks, so not just a single best guess. And we really want to be able to produce outcomes that are merely possible. It may be that policy, as Raphael was suggesting, and as I think Alan was suggesting, it may be that policy, the most important thing for policy is not what we think what will happen, but things that we think not only could happen, but just might happen with the merest possibility. And it'd be nice to have some framework for generating that inside of a single coherent model. So I'll try to be concrete about what I mean by that. So the first recommendation is how to run climate models. So Raphael was touching on the point that, and Alan also touched on it, that traditionally these models have primarily been run in best guess mode. They're really complicated. They take a long time to run. You want to run them for a handful of emission trajectories. So there's a limit to how much you can explore the model space or even the parameterization space within a given model. I'm going to argue that for economics, that's less useful than actually pushing the models to their boundaries and seeing what would happen in the tails. So I almost wouldn't, if there were a new model, I almost wouldn't want to know its best guess. I would want to know what its most extreme behavior could be, because that would be more informative to me at this point. So what's merely possible might be more valuable for policy than what's most likely. So a brief cartoon of what I mean, and I know this is a real oversimplification of the way that distributions are currently constructed and the debates around model democracy, but nonetheless, we'll go with it. So there's a set of models. These models can generate different parameterizations that give different output. It may be that each model has one parameterization. It may be there's a handful of models with a handful of parameterizations. These parameterizations can be weighted against their ability to replicate the historical temperature record. And then from that, you might be able to get some sort of probability distribution of future warming as some sort of weighted frequencies of model output. The problem with this is that there's going to be biases that are present across every model because models are constrained by sharing code. They share basic scientific knowledge. They just hit the constraints because what we know today. On top of just the fact that they're generally calibrated for best guesses, so they're not even being pushed to explore the boundaries of what the model could say. And it also may be true that prioritizing models that replicate the past may not be the best way to figure out which model best predicts the future when we're going out of sample with climate change. So what I think we would really value as economists, speaking for a group of people, is a simple tractable models of Earth system responses. So we're going to use models for two purposes. One is to do math with pen and paper. The other is to do math with computational models, where we're often going to be having to call the model a whole bunch of times. Either way, we would need a simple enough model. And even if you get some sort of non-parametric probability distribution, fitting a name distribution to it would be super helpful for actually then using it in computer code or in pen and paper mathematics, at least knowing roughly what shape it might follow. So this is just summarizing stuff I've already said. The other thing that we could use a lot more focus on is the evolution of uncertainty over time within the model. So I've talked about how we really care about today's uncertainty and getting a better picture of that. But also think about, imagine that we don't know warming per unit of carbon dioxide. So we can get a sense of some of that range from the range of model output. But within a given model, how would the scientists living in the model update their beliefs over time? Right now, economists do think about that. I mean, this is an important part of dealing with uncertainty, is the ability to course correct. But we're basically making up learning frameworks because there is no benchmark framework or study from the science literature that at least that I'm aware of. And so I think formally investigating this with more complex models to tell us how you think scientists in the future would update beliefs and whether it would be fast or whether it would be slow would prevent us from, we're not going to just ignore it, but we're just going to make something up in the absence of having something from the scientific literature. So I think that would be a helpful set of experiments to run. Second, tipping points. So a few of us in the call have worked with tipping points at various times. I would say that the two things that we've had to kind of make up without better guidance in the scientific literature are what do tipping points mean mathematically, because we've got to do something with numbers and with algebra. And the other is what are the probabilities attached to these tipping points? And sometimes there's better guidance, sometimes they're less. When I worked on this a while back, the best guidance I could find in terms of probabilities was a color-coded diagram like this, and I had to somehow convert this into a probability distribution. It may be that you think it's ridiculous that we can get probabilities for anything like this. That may be true, but nonetheless, we're probably going to need them at some point, so it might as well come from the scientific community rather than come from economists effectively making up probabilities. I mean, obviously there are ways to do probability-free approaches, but giving us your best shot, your best subjective distribution is still not a crazy thing to do as the experts. So again, we're going to make stuff up without actually having the models from the scientific community, so please give them to us. Simple is fine, probably even preferred. And what would be really great is that the past attempts to deal with tipping points are a little ad hoc. The tipping points are kind of grafted onto the climate system or onto the economic system. It would be nice to have a simple modeling framework that successfully captured main stories from climate science, but something internal to the model framework could generate tipping behavior based on either a parameter whose value we don't know or based on the possibility of shocks to the system. But if tipping points could arise, whatever we mean by tipping points, if we were given a framework where that framework could itself produce the tipping points we're worried about, that would allow us to do something much more real rather than sort of making up our own formulations. Forecastability, so turning into the economic impact side. So what does climate change mean for the economy? The main way that economists have come to approach this question, and I put no in scare quotes intentionally, is that we study the impacts of weather, so like one-off weather shocks. They're effectively surprising. They're good, what we call natural experiments. And then you can see how they matter for mortality or for economic output or for anything else you might care about, for productivity, for hours worked. And then we'd like to extrapolate that to the cost of climate change. There's major issues. One of them is just people are going to understand things about climate change much further in advance than they will for a one-off weather shock. But in order to kind of close this gap, we need more guidance from the scientific literature about forecastability under climate change. So one thing we'd like to know, which I know there's been a little scientific work on, although I don't know that there's a consensus answer yet, is how will climate change alter the variance of both local weather and of seasonal climate? And I think really the economic angle on that is how will forecastability change? So this is going back to the title of the slide, what will we know, when will we know it? For economic actions, it's going to matter not just how the realizations change, but whether we knew that they were going to be different well in advance or only barely in advance or not at all in advance. So a picture of what I mean is that imagine, let's say hypothetically, that the variance of weather will be altered in the future due to climate change. So just things are going to get noisier. There's going to be more extremes at both ends, let's say, around the mean. So some of that variance is going to be revealed in seasonal forecasts. So we might know 4 months ahead that this winter is going to be especially cold or that this winter will be especially warm. Some of the variance may not be. It could go either way. It might get better, it might get worse. Some of the variance is going to be revealed in run-of-the-mill forecasts 1 day to 2 weeks ahead. So sure, we might get more extremes, but if we see them coming 2 weeks ahead, they might matter very differently than if we don't see them coming at all. So I think what we'd really like to know as economists is not only will the variance of weather change, but how will that variance be apportioned on the different timescales at which we might anticipate the altered weather? There's very different economic implications to saying that seasons are going to have more variance across them, but we're going to know it when we get there, versus saying that the weather on any given day is going to have a lot more variance, and we're going to be surprised by it when we get there because our forecasts are going to be a lot worse than they are today. And I've seen, I think, literally nothing formal about this from the scientific literature. Doesn't mean it's not there, it just means I don't know about it. Which brings me to my next point. There's a lot I don't know about and a lot that most economists don't know about. We have full-time jobs. We're just trying to keep up with the economics literature, and not just the climate economics literature, I mean like the broader literature. And plus we need to know, not only find and happen to see the relevant climate science literature, but we need to actually know whether new research that we happen to read is widely accepted or not. Like if a new framework comes out, maybe this framework might be compelling. It might be really tractable and even something that we can do pen and paper math with, which we would love. but we need to know whether this is one paper or whether a lot of people agree that this is kind of a good thing to be doing. So what I think the community could do more of is actually translating new developments for social scientists. And so this isn't quite at the level of the IPCC. I think it's a little bit different. Like I haven't seen the IPCC chapter that would do quite what I have in mind. This would be giving us a suite of mathematical frameworks that, and will they be both telling us what is the relevant new research, like what do we think is a big picture importance in the scientific community, and to what degree do we think people actually believe or firmly believe it's true versus have questions about it. And also evaluating a set of mathematical frameworks that we could use. So I'm thinking of this as what I'm calling a simple MEP, so somewhat imprecise modeling for portability into economics. The idea being take a range of mathematical frameworks of different complexities or different calibrations, and instead of finding maybe one that best emulates a climate model, run a whole bunch of them through their paces in a whole bunch of different dimensions and just tell us how well they perform. Because for some applications, we can use more complex frameworks and some we can't. Some applications we're going to care about capturing one aspect of the future, and some applications will care about capturing another aspect of the future. You know, a paper on tipping points might need one kind of model, and a paper on uncertainty about warming might need a different kind of model, or a paper that's not about uncertainty at all might want a different kind of model. So I think, I know there's been a push to like advocate for certain models like FAIR, for instance. I think it's much more helpful to give us the information to let us choose the model for an application. And this would make, if this were updated over time, this would more quickly translate climate science into economics and social science research. So it's just repeating what I already said. And again, a lot of our focus is really on qualitative behavior because we don't know all the relevant numbers to really generously or truly give a single numerical estimate. So I think focusing on the qualitative performance of the various simple frameworks it would be especially important. So summary is mostly repeating stuff I already said again. So climate economics is messy, but you know there are some things that I think we could get from climate science that could actually move the needle. In particular, more exploring the model space of just how bad things could get and how, you know, some sense of how likely it might be, not just what the most extreme possibility is. Would we learn things are getting bad and we still have time to course correct? Hugely important for thinking about today's policy. And really, this question of just to what degree the surprisal, the relative surprisingness of the weather is going to change week to week, season to season with climate change. Maybe not at all, maybe a lot. Like I really don't know. I could tell a story either way. It would be really nice to have an answer from the scientific community. Otherwise, contrary to reputation, economists prefer not to make things up. We prefer to use data. But in accord with reputation, where there is no data, we are not scared to make things up. So please help us not do that. So thank you.
All right, thank you, Derek. Again, if you have questions, put them in the chat or raise your hand. And let's see, it sounds like you outlined a major research endeavor for the climate science community. So before we embark on this, I want to know, is this your opinion, or is this an opinion that's shared by everybody working this space, or is this an opinion that they would all have if they were familiar with the problems with climate models as you are?
This is my opinion. I haven't surveyed anybody.
What do you think?
Do I think other people would agree with me?
Yes.
I think there are other people that would agree with each point I've made. Whether anybody would agree with all points or has thought about all points this way, I wouldn't hazard a guess. But I have had conversations with, I don't think these are completely idiosyncratic. I'll put it that way.
All right, thank you. Raphael, I see you have your hand up. Go ahead and ask your question.
I can also help. So as another climate economist, I can help answer by saying that I will happily have Derek speak for me on all of these subjects. I think I agree with everything, and to the extent that other climate economists may not agree, I feel like more of them should.
Okay, thank you for delegating authority to me. I appreciate it. I'll also execute your will if you'd like.
Derek, at the beginning of your talk, you effectively criticized climate science for focusing on these small degrees of sensitivity when they're really not the important question for economists. I wonder if I could pose a similar criticism, or why do economists worry about these dollar differences when the international community seems to be saying, let's target 2 degrees and maybe 1.5 degrees?
Yeah, I think that's a very fair question. So first, let me refine what I said earlier, at least the way it was interpreted a bit. I don't think it's wrong to ask those questions and to focus on refining those estimates. Like, I think we do need to know the answers. I think as a user for particular economic questions is not the most valuable kind of analyses to be doing. It doesn't mean there's not broader social value to it, right? Like the value to academic economists is not the value to overall society. So I'm going to be very clear about that. Those things do not move one for one. In terms of economists, it's true. Like there's a lot of economic almost obsession with what's the right tax to levels of 10 to 20 or $30 ranges. There's a question whether all the work we're doing on the optimal tax matters at all, given the framing in terms of temperature targets. We have to push forward with knowledge, and I think there are. It is true that when you look at like the government social cost of carbon estimates, like they are rooted in the economic model's quantitative estimates, whether that's a good thing to do or a bad thing to do. I personally don't like using these models for concrete numbers, but I understand as a policymaker, if you don't want to be seen as arbitrary, it's nice to be able to outsource the number and just rely on an outside model from an academic to tell you. So I don't think it's a crazy thing from a political economy perspective. In terms of temperature targets, I don't know that I would describe those as being the result of a climate model. It's true that a lot of the push for temperature limits does seem to have come from the climate science community, but I don't think I've seen anything in a climate science model that really says that one temperature target is the right target versus another target. I think there's pros and cons of taking a temperature target framework, and it's going to be way too deep to get into here, but I do think that there's the refining of exact temperature projections. I don't know that I would call that the main driver behind the temperature targets, but maybe it is. I don't know.
Okay, thanks. Mona?
Fabulous. Thank you again, Derek. That was fantastic. As we heard from the speakers, I'm thinking about interdisciplinary education that we should provide to our graduate students and cross-pollinate those ideas. Moving on to our next speaker, Dr. Raphael Calel. Did I say your name right this time around?
Calel or Salel is how my parents pronounce it. Calel is how I do because it's easy.
Calel it is, Dr. Raphael Calel, who is going to talk about the economics of global climate variability. Raphael, take it away, please.
Great. So this is work, so I'm a climate economist. This is work written with David Stainforth, who is a climate physicist. So I hope that I find that interdisciplinary collaboration is essential to sort of understanding these points, and I take a lot of the physics here is coming from him. It's based on some work that we did also with Sandra Chapman and Nick Watkins. It was published in Nature Communications, so you can refer to that for even more details. So what we're doing here is sort of I'm going to nest it within some of the concepts earlier. So we're looking at an integrated assessment model of climate change of the kind that Bill Nordhaus won the Nobel Prize for. Here's an even simpler schematic of what it does. It's sort of a climate model and an economic growth model coupled together with some kind of damage function and abatement function that sort of links those two things together. And then you optimize. Now, the climate model in something like Bill Nordhaus's DICE model, if you look at what is the temperature forecast, if you put in a certain temperature trajectory, it looks like this. So this is an RCP6 temperature forecast. And the thing to notice about it, that we noticed about it in this paper, is it's just a sort of smooth curve. And if you look at any historical or model-based temperature time series, they are jumping up and down all the time. And if we're thinking about whether that matters or not, then we need to have a climate module inside of our economic models that actually reflect that kind of behavior. And so what we did, so some economists have sort of just taken this kind of RCP and done some kind of white noise thing, but we took a stochastic energy balance model so Klaus Hasselmann just won the Nobel Prize last year for this kind of work, and we integrated that into our integrated assessment models, which gives us this sort of orange line jumping up and down, and it behaves quite differently from white noise. This will be important later on, but sort of you can see that it's quite possible to depart from your trend for a decade or 2 decades at a time, not just sort of 1 year or 2 years. And so it behaves quite differently than sort of the very, very simple way that economists have done it before. Now, if you take lots and lots of runs of this model with stochastic temperature time series instead of just the deterministic one, what happens is you get a whole distribution of climate damages instead of just a single number. So here in this, the particular numbers are not very important here, but what you see is that sort of instead of the single number, which in the middle here, which is for the deterministic case, you get a distribution where like the 90% confidence interval, it can be like as much as sort of 30-40% higher than the deterministic model, or maybe 20-25% lower than the deterministic model. So like the range of possible damages really increases a lot, and the probability that you get these extreme damages is quite high, actually, sort of uncomfortably high. And yeah, and so one thing that we have in these sort of economic models is we have a decision maker that is averse to risk, that they're usually built in a way that we don't like risk. And if we use that kind of setup to figure out like how much would this decision maker pay to avoid all of this variability, what if we could buy the smooth curve instead of having to face sort of the jumping around global temperature, turns out we would pay something like maybe 20% of current global GDP to avoid that. Now, in practice, we can't, this is not a choice. This is not, there is no insurance policy that we can buy, except for the closest thing we can get is we can sort of buy adaptation to extremes. So if we can pay for adaptation, this is the kind of thing that we might want to do, and we might be willing to pay quite a lot for that. Now, there's another kind of uncertainty. And so here, all we're doing is, so going back to Charles Manski's presentation, he was talking about sort of model uncertainty. He was using different terms, but the way that I think about his uncertainty is like uncertainty about what the right model is. And then what, conditional on having the right model, then there's uncertainty about what are the right parameter values. That's what I call, I refer to that as epistemic uncertainty. It's knowledge about the parameter values. And then conditional on knowing the model and knowing the parameter values, there's this thing called aleatory uncertainty, which is the jumping up and down from year to year, the sort of thing that is unpredictable because it's a stochastic system. So even if you have perfect knowledge of the model and the parameters, you're still going to get surprises. And so what economists have mostly dealt with so far is what I refer to as epistemic uncertainty. So we assume the model is right, but we don't know the parameters for sure. So something like the climate sensitivity, there's some distribution, we don't know what it is. We can simulate out our model, lots and lots of different climate sensitivities. This gives us a distribution of social cost of carbon. This is what the US government does. These are just, but what you see here is that all of these trajectories are themselves smooth. So we assume that there is uncertainty about what the parameter value is, so we don't know which of these lines we are on, but each of the parameters, each of the sort of lines is a smooth line once you move along it. And what you could do is you can add white noise, and some of that has been done before. It is very convenient when you're trying to solve a kind of Bayesian learning problem, but it isn't quite a physical way to do things. And so we did the analysis with the stochastic energy balance model instead. And the interesting thing to note here, the sort of, is that there's an interaction between the epistemic uncertainty and the aleatory uncertainty. So what's happening here is that this gamma parameter, this is the feedback parameter in the model. So it's inversely related to the climate sensitivity. If you happen to draw a high climate sensitivity, that means that you're going to be on a higher path, but it also means that you're going to get an amplification of the noise. So you can see here, these are 3 different sort of ensembles of an energy balance model run with different climate sensitivities. And so here you have a positive interaction. So if we have a bad draw from the distribution in terms of climate sensitivity, not only are we going to be on a higher average temperature trajectory, but we're also going to be in a more variable world. And so we get sort of this double whammy effect that is unfortunate from an economic perspective. And that is something that you can't see at all unless you sort of have a physical representation of how the uncertainty behaves. And when we do this, again, sort of numbers, as Derek suggested, are like always at the risk of being overly precise in these contexts. But what we see is that at least to an order of magnitude, it looks like the interaction effect is probably as big as the primary effect of the aleatory uncertainty. So you're getting sort of the uncertainty on along a single path, but then the interaction between uncertainty over the path and the amount of uncertainty in that path is going to sort of double that total effect. And we're talking here, I mean, in our estimates, it depends on lots of assumptions about discount rates and damage functions and those things, but sort of based on our sort of conservative assumptions, we're getting things that are measured in tens of trillions of dollars. This is about 40% of global GDP currently. And we did it for a bunch of different scenarios, so we can get sort of as low as 10 trillion, as high as 50 trillion. If we make different assumptions about discount rates and damage functions, you can easily get to hundreds of trillions or thousands of trillions. So like, I don't want to put too much emphasis on the numbers, but I think what I'm trying to say is that having sort of a physical understanding of the nature of global climate variability in these models is going to make a big difference to whatever your baseline is. It's going to increase your damages significantly. Now, I want to make a comment on this point about social cost of carbon. So what we're doing is we're measuring risk premiums, which is basically like how much would you pay to avoid this kind of uncertainty, which is a different exercise to what social cost of carbon exercises is. Social cost of carbon is thinking about how much damage would result if you emit a marginal ton of carbon, or how much damage would you avoid if you avoid that ton of carbon. And the difference here is that mitigation moves where you are along the sort of damage function, but it doesn't really do much for the variability of the climate. So it sort of puts you in a lower section of a curve, but it doesn't actually reduce the variability very much. And so if you just look at, if I put out 1 more ton of carbon, how much more variability do I get? Not very much. And so actually the effect of this thinking on the social cost of carbon is very small. So this isn't really about changing our analysis of mitigation very much. What this is telling us is, even though it doesn't have much effect on our mitigation policy, having this included would tell us a lot more about how much we've underestimated the value of adapting to extremes, adapting to variability. And so the numbers that we're thinking about have much more to do with adaptation than they do with mitigation. And they are outside of the sort of conventional analysis. So they haven't been analyzed previously. Right, concluding, incorporating a simple stochastic climate model into an integrated assessment model adds trillions, possibly many, many trillions in climate damages. To be clear, that is a second order effect of climate change, but it's a pretty significant one. The effect on the social cost of carbon itself is likely to be small, but that's because variability is not really avoidable through mitigation at the margin. So the risk premium provides a different rationale, and it's for thinking about climate change, it's more about investing in adaptation. And so in terms of speaking to the scientific community, what would be useful for sort of making improving our analysis of what would be the appropriate investments in adaptation would be to develop a better understanding of the nature of the variability that we are trying to prepare for. And so right now we're using some very simple climate physics, but thinking about what are the higher order moments of the distribution, like are the representations we have enough? And I'm thinking here in particular, going back to Derek's point about tails, and actually also to Charles' point about sort of minimax regret, the tails could matter quite a lot here. So thinking about what are the higher order moments, thinking about the autocovariance structure of temperature is really important. It's not something that economists have been very good at thinking about, but understanding it is really important, because having a 20-year drought versus having every other year drought for 40 years is very different from an economics perspective. So understanding the autocovariance structure is very important. And then mapping global extremes to local extremes. So not necessarily that we have to know what is the distribution of temperature or precipitation in Washington, D.C. in 2050 or 2100, but conditional on the global climate being this, like what would be the local conditions? So like having more conditional predictions, I think would be the kind of thing that would allow us to make better planning, because certain like global characteristics are easier to forecast ahead of time. And so understanding what is the mapping between the global and the local conditions, conditional on having a forecast of the global conditions, we can update our local planning. That would be very useful. And in addition, I agree with everything that Derek said.
All right, thank you. Let's see, again, looking for questions. I'll go ahead and ask the first, but first a comment. I really hate living in a world where an error of $10 trillion might be considered to be too precise. But also note that the long-term variability in climate models is actually fairly poorly validated, and it may be substantially off, particularly on a regional scale, like things like the North Atlantic oscillation that will drastically affect European temperatures and decadal timescales. And you're saying, even though we know we're doing bad at this, we really need to focus on improving it because it's really important?
Yeah, I mean, I think that, well, I wonder, so maybe this is me being just ignorant, but I think that having more sort of, for me, it's more the conditional prediction. So conditional on like, so knowing the sort of the boundary conditions at the time. So I know that we don't know what are the sort of global average temperature 100 years from now. I know that we don't know what is the continental average temperature. But if we knew the continental average temperature 100 years from now, could we, conditional on that, put more constraints on what we expect at a lower scale? So it's more sort of thinking about putting conditional on global conditions at the time, as opposed to conditional on what we know today. And so I'm wondering whether that kind of behavior within a model is possible to explore, because mostly what I see are people trying to provide unconditional projections, conditional only on emissions and nothing else.
Okay, thank you. I don't see any other questions, so Mona, please take it away.
All right, thank you so much. So we'll switch gears here a little bit and move from economics to the health sector. Thank you again, Raphael, for that amazing talk. We'll go now to Dr. Kristie Ebi, who is going to talk about the use of weather and climate data to model and forecast vector-borne diseases. Kristie, take it away. Thank you.
Thank you very much. And I'm going to have to ask Jenny if you can share the slides that WebEx is refusing to let me share. And as Mona said, we're going to be shifting gears, and I'm giving this presentation on behalf of Corey Moran, who was unable to join today. So I'm a poor stand-in for Corey, and we are going to switch to thinking about using weather and climate data to forecast vector-borne diseases. Next slide, please. Vector-borne diseases are diseases that are transmitted to humans or other animals by a tick, by a mosquito, or some other living organisms. There's other kinds of vectors that are involved in vector-borne diseases. The figure shows you some of the vector-borne diseases of concern. Most of my focus today is going to be on dengue fever, which is number 3 in the list you see to the right. But there are lots of vector-borne diseases that cause significant burdens of disease around the world. Next slide, please. When we think about vector-borne disease, we are looking at a system, that there's multiple components to that system. It's not just the disease and the vector, but also the interaction with our natural systems. You can see on the right, there is interactions between the host, the agent, and the environment. So thinking about how to do the modeling to provide useful, usable, and used information in being able to forecast when there could be disease outbreaks requires understanding of all of these components and how they interact in ways that in some cases are surprising, but we do have to make sure that we follow those interactions to be most helpful in our forecasts. Next slide, please. When we think about infectious disease transmission cycles, we look at both human and animal diseases that are involved in that transmission cycle. You can see there's direct transmission of disease in the upper left between humans. COVID-19 is the one that comes to everybody's mind at the moment. On the right, we're going to focus on indirect transmission, where there is transmission between humans, but you have to have some kind of vector. You have to have a mosquito or a tick involved in having that pathogen go from one human to another. We're not going to talk about zoonotic diseases, but they're just important to note there's a lot of zoonotic diseases, and many of the diseases that cause significant burdens in human populations arose in animals. Next slide, please. This is just a heuristic about the mosquito life cycle, noting that mosquitoes, like so many other organisms, have multiple stages, starting from eggs, going through larvae to pupae to full-grown adults. You'll also see on here that it's the females that bite, therefore the females that transmit disease, because the females need the protein in blood to be able to lay their eggs. Next slide, please. And temperature affects pathogens. So we think about pathogens. This particular example is for 2 of the pathogens that can cause malaria. There's similar graphs for dengue, for other vector-borne diseases. And I'll talk in a moment about the impacts of weather on the vectors, but specifically on the pathogens. Once they get pulled into the gut of whatever tick we're talking about or whatever mosquito we're talking about, there's something called the extrinsic incubation period. And it is an estimate of the time required for the pathogen to develop inside the vector, replicate in the gut, and then migrate to wherever it's transmitted. So salivary glands for mosquitoes. And that extrinsic incubation period is temperature dependent, as you see on the right. Temperature also affects the pathogen load. So how much of the pathogen are you going to see when that mosquito bites somebody else and injects through the salivary glands these particular pathogens? We have to take these kinds of dynamics into account because they do affect their survival within the mosquito, within the tick, and of course in the environment. Next slide, please. Temperature affects the host and it affects the vector. You see 2 figures on the right. The top one is larval development rate per hour. And you can see that larvae, so this is for mosquitoes, develop much faster at higher temperatures. But when we get to high temperatures, there's a real fall off in that development. So this is not a continuous curve with temperature. You have to take into account that low temperatures and high temperatures can be lethal for larval development. The bottom figure shows the proportion of larvae surviving to the pupa stage. And again, you can see this real temperature dependence, that there's temperatures where it's more ideal and temperatures where it fails. And when you do the modeling, you have to take into account that high temperatures are associated with lower disease transmission because the vector is affected at these very high temperatures. We know that temperature affects foraging, feeding, seeking shelter. We know that mosquitoes are living beyond the range that you'd think they'd be able to live in terms of the environmental condition, because they go and find a place to sit when it's too hot. They find places where it's too cold outside, where they find places where they can shelter. Temperature also affects the population dynamics, as I've talked about with these two figures. And so this is part of what we have to determine when we work out an early warning system. Next slide, please. Dengue is a disease that's carried between humans by Aedes mosquitoes. The one that's most common in the US is Aedes aegypti. If you are afraid of mosquitoes, then Aedes is a mosquito to be afraid of. It survives around humans. It's completely adapted to our environment. It will fly a mile to bite a human over anybody else. There's about 94 million symptomatic cases of dengue fever every year. The estimate is there's around 300 to 400 million cases of dengue annually. Most of them are asymptomatic, but it is the most common vector-borne disease in the world. The symptoms, as you can see, are fever, headache, rash. It's a pretty unpleasant experience for people who have symptomatic cases. You can actually get dengue 4 times. There's 4 different serotypes, and there's not immunity across one type of dengue to another type. And we know that dengue is increasing its geographic range with climate change. As temperatures become warmer, more habitat is suitable for Aedes and is moving into places where it hasn't been for a long time or is new to an area. We know we've got local transmission now in the US and Florida and in Texas. Next slide, please. And just like the other figures that I showed, climate influences dengue risk. That the survival of Aedes is similar to about 32 degrees C and is affected by relative humidity. And so we need to take into account both temperature and relative humidity. Mosquitoes typically benefit from higher humidity. The extrinsic incubation period is much shorter at higher temperatures, and so you've got much greater possibility of transmission. And you've got to combine these to calculate the rate of mosquito survival through the extrinsic incubation period, because there's combinations where you can have high transmission, you can have high replicability of the pathogen, but the mosquito doesn't survive long enough to be able to transmit the disease. So putting these factors together is required for forecasting systems. Next slide, please. And this is a summary figure from work that Corey has done looking at weeks suitable for dengue transmission in the Americas, where the blue is where you just don't have weeks that are suitable. The dark red shows you the areas where almost the entire year is suitable for transmission. And you can see in cooler climates, there's a seasonality to dengue transmission or the possibility of dengue transmission. Next slide, please. And this is where early warning systems come in. When you have that kind of seasonality, you can use early warning and response systems to help identify when you could see an outbreak of dengue fever. When everything aligns, that you do have transmission, it's possible to have diseases occur. And these two figures show you on the top the difference between a passive surveillance system versus no surveillance, showing a typical kind of outbreak curve, kind of a bell-shaped curve when there's no surveillance. When you have at least passive surveillance, you can start detecting cases earlier, put in your response faster, reduce the size of that curve, thereby reducing the number of people who come down with dengue in this case. The bottom figure shows what happens when you combine that with surveillance. And using environmental information, understanding these relationships between temperature, relative humidity, the vector, and the pathogen, you can then work out conditions where you're likely to have an outbreak. And this shows you that you can then start so much sooner, long before you have the outbreak, to put in place a variety of public health measures, warning pregnant women, cleaning up breeding sites, taking a variety of actions to help protect the population from an outbreak. Singapore has got the best dengue control program in the world. Singapore either has initiated or will soon initiate an early warning system based on environmental information that will give 4 months warning. And so there's a lot of potential then having that much warning to be able to really reduce the size of an outbreak. Next slide, please. And this puts us all together into how to think about developing an early warning and response system. In the interest of time, I'm not going to go through all of these steps, but you can see that just understanding the environmental conditions that drive outbreaks then needs to be paired with how do you communicate this information to the public in ways that's taken up by communities? How do you put in place effective intervention plans? Make sure that you've got the human and financial resources to be able to manage additional cases, and put all of this together into a system so that you can reduce the number of negative health outcomes. Next slide, please. And there's challenges. We've heard quite a lot of challenges for the last few minutes about using weather and climate data, particularly in forecasting disease risk. There's multiple sources of uncertainties in terms of the accuracy of the models. We've heard a lot about models and the challenges with using models, the accuracy of our forecasts, the accuracy of our epidemiological models. And so when we're looking at using weather and climate data to develop forecasts for disease risk, we have to pay attention to issues in addition to what I just mentioned, but issues such as timescale mismatches. And that comes up quite often because health data may only be collected every week. You've got hourly weather data. How are you going to start matching up these timescales? Looking at the spatial mismatches between administrative units versus gridded weather data. Thinking about what the appropriate simulations and scenarios are to use when doing a forecast. And then, as we just heard, thinking about forecast anomalies. And what do we do when there's quite a significant anomaly? How do we incorporate that into our forecast so that we can provide the most useful information to protect and promote health? And with that, thank you very much for listening, and I look forward to a few questions.
All right, thank you. So we've gone from the very general cost-based framework to specifically looking at another system through a dynamical framework and how those things evolve over time. Is there a need or a push for essentially having a disease model fully integrated into a predictive weather and climate model so that the evolution of the disease is being simulated with the information that's available within the model itself at full resolution?
That hasn't been attempted yet because of the challenges of integrating across disciplines. And there is potential for having greater integration in terms of how you can do what you just suggested, but you also have to integrate all the operational aspects to make sure that you can reach the various communities you need to reach to, that they understand the information that's being presented, making sure that we do whatever we have to do to make sure that this information is taken up. Because we all know the challenge of having really accurate weather forecasts and some people just not paying attention to them. So we have to think about the end-to-end aspect of this. But good question, thank you.
And I suppose another challenge, as we've seen this past couple of years, is that epidemiological forecasting is really difficult as well. And there's an inherent unknown aspect to how a particular disease will evolve in time, even if you know everything you need to know on a macro scale. Is that correct?
It is correct. And one of the issues that Corey didn't raise in here is when we think about developing these kinds of epidemiological models, that there's essentially two different approaches, and it's very similar to what people do with weather and climate data. Do you start with the observations and build your model from the observations? But for our case, the observations are confounded by where do you already have disease control programs? What kinds of actions are already in place? And so you can actually find regions where there's no cases, where in theory there should be cases, but the public health program prevents that. And so you get false negatives. You can start, as many of the models are done in weather and climate, from first principles of what do we understand about the dynamics of the system, what do we understand from laboratory studies, and use that to build a model that way. And they both have benefits and they both have constraints. And you need to really use both approaches to get a better sense of what could be the best advice you can provide to communities.
Okay, thank you. I don't see any other questions. So Mona, please introduce our last speaker.
Great. Thank you. Thank you so much, Dr. Ebi. So we're bumping against time, everyone. It is 2:30 p.m. We're a few minutes behind time. If it's okay with our next speaker and all of you, we're going to continue with our last talk of the day, which is by Dr. Nathalie Voisin. And she's going to talk about a two-way street: interdependence of climate variability and change with human systems. Dr. Nathalie, please take it away. Thank you.
Thank you so much for sticking around, and really on behalf of all of the co-authors here that I really acknowledge, I would like to thank everybody for the opportunity to present on this article that we put in US Climate Variations. And I will invite all of the co-authors in joining me address any of the question at the end. The overarching objective of this article and this presentation is really to present an emerging science called multi-sector dynamics and outreach to the Cliver research community on brainstorming how to work together synergistically moving forward and advancing our research. So what is multi-sector dynamics? It comes really from the simple observations that we lack a basic understanding of how human Earth systems shape each other across scales of variability and how this dependency and feedbacks vary with time. So throughout the article, we are introducing the concept of multi-sector dynamics to address this challenge. We're then illustrating MSD main science themes through two case studies. We're discussing on how to reach multi-sector dynamics community, and then we outline the potential synergies between MSD and Cliver, and most important, propose ways to engage in collaborative activities. And over the next couple of slides, I'm just going to provide a summary, the highlights. So first, the concept of MSD. You can see here on the left, we have the Earth and the environmental systems, and we have the human systems, the built systems. We have the social economic systems and governance systems. All of them combine those. This is the world where we live today, and we're trying to projections on how those systems are going to co-evolve. So MSD is really the study of those built, natural, and socioeconomic systems and how they co-evolved in response to change. Now, what is change? I think we've seen in previous discussions about tipping point and so on. So this is what you can see on the lower right corners, just some concept that we are adopting to even describe what is change and the different phases of growth accumulation and then disruptions, and understanding when a system is challenged but comes back to initial states or evolve to a new state, and how that works across different systems. So we have human Earth system feedback shape interdependent pathways of societal change across scales and uncertainties. So those are really the main concepts behind MSD, and we need this science because there's a lot of concept, a lot of extreme events that we have seen in the community that we still don't understand at this time. And none of the other science are addressing those points. So we have science themes that are central to MSD. Naturally, we're going to find dependencies and interactions, how to define them, how to project them. What are the disruptions and uncertainties? And we saw a lot of those examples actually earlier today. Adaptive human actions, and of course, model coupling and evolution. A lot of the main principle of MSD is fair science, and we're looking in new ways to do model couplings and making sure that this is open source. So the outcomes of the science include data sets, methods, modeling platforms, use cases, and as well programs for education for the new generations of scientists. Might still be very abstract, so that's why in the articles we are providing 2 examples, 2 case studies to talk about what is MSD, even with all of those concepts. So the first one is a case study by Voisin et al. In 2019. It's a qualitative study that discussed the concepts about dependency and interactions and model coupling and evaluation. And in this paper, it's what you can see in the figure. It's the descriptions of the phase of resilience to describe the evolution of the electricity sector in response to disruption in the water sector across scales of dependency. And what we can see here is that they are at the scales of human systems, end user, plant scales to aggregate scales to institutions. There are different ways of characterizing the change, and there are different phases of evolutions and adaptations and mitigations. And here, this is just across 2 sectors. In the second case study, it's becoming more methods and quantitative. It's a paper by Quinn et al. In 2020. And the paper is looking at disruptions and uncertainty and specifically adaptive human actions. The paper looks at alternative framings of hydroclimatic variability and specifically looks at how different definitions of water availability disruptions could lead to different human adaptive pathways. And so this is also pretty important as we are defining mitigations and understanding how human systems are evolving. There are multiple concepts that need to be considered. So we have multiple case studies. The point is where can you find people doing multi-sector dynamics? DOE Office of Science is presently spearheading a number of multi-institutional projects that are analyzing systems, transformation, and transitions. And you can find a list in the article. They're all looking at transformation and transitions across sectors. On the left side, this is just the figures that summarize. So this is a really high-level summary of all of those different projects. And we have the different timescales, spatial scales, sectors, and systems. The point is that all of them have the Earth system component. They all rely on advances in climate variabilities and uncertainties and how this co-evolve or trigger changes in human systems and co-evolve with human systems. So the point here is the link with the US climate research community is that MSD really relied on that collaborations with US climate. So on the lower left here, you're looking at the type of research directions that we have identified, where we would love to engage even more with US climate. Climate variabilities and uncertainties are the first one that we already mentioned. The predictive skill is also very important to understand preparedness and how those phases are going to evolve. If you already know in advance what's going to happen. New dynamics, human systems are now driving a number of Earth systems, and there are different scales. So how can human systems and adaptive human system inform the climate and ocean system research? We have modeling platforms and open science that we are working on, and we can work synergistically as well. How can we work together? Use cases, webinars, working groups, and joint sessions and major geophysical conferences. So I really want to point out the multisectordynamics.org that you can see on the screen. This is where you can find a lot of the descriptions of the different projects, but also the working groups who are absolutely open to any other communities to work with us on some subjects of interest at this time, and then it evolves. So we also encourage people to promote and suggest new working groups. And there's also ways to provide feedbacks and point of contacts for exchanges. So really the opportunity here for MSD is to promote and extend the MSD datasets and modeling capabilities of human system interactions with the climate and ocean system research. And what we think the value proposition for the US Cliver is working with MSD to extend regional and sectoral application to US Cliver research. So really want to bring forward again, just to put more faces on that multi-sector dynamics research, is bring forward the community of practice that is led here by the community of practice facilitation team and is part of the co-authors. There is also a science steering committee, and together with the other projects, the community of practice is constructed by the people, for the people, as long as the science questions are relevant or we're moving to new directions. And in this report, where there will be a soft publication next week, it really details more motivations for multi-sector dynamics, provide even more case studies to understand why and where it's useful, and scope the science in terms of methods, models, educational programs, and most important, the outreach to community on how we can work together. So really recommend you to reach out and have a grasp at this report. Thank you.
Well, thank you very much. That's a very exciting project. And you're not the first presenter today to mention the importance of knowing predictive skill and future changes in predictions at different timescales in order to be able to model societal responses. Can you talk a little bit more about that, please?
Yes. So we do have a number of examples. Let me go back to that. I think that slide that goes on this one. So we do have a number of examples. I think it's more that we had the previous discussions with health system, for example. We want to understand what are the tipping points. I think that goes back to some of the societal change before. All of those previous discussions were addressing. I think it relates to some of the same concerns and the same passions that we have in MSD. The societal change. We want to understand, I'll try to find a more concrete example out of the many we have. With energy transitions, for example, that's the one I'm the most familiar with. We've been looking at a very long time at expanding the grid and making sure that it would be, that was for resource adequacy. But more and more, as the society is changing, it's not just economic. It's really human systems and the human sciences, where with climate change, it's actually driving policy and it's driving a shocks in how we are looking now the future grid. So we were looking at energy transitions that are going to change a lot of our projections of the infrastructure in the future. And on top of this, the society has changed even more, that we are putting, for example, equity, environmental justice and equity on top of those changes. And those changes that we were not seeing in any of our mathematical models before are going to change how Earth and environmental system will be in the future, or how we're going to prepare to extreme events as well. So this is more the societal impact, and also including the society as an active agent of decisions, not just impact again, but really understanding how they shape all of the human structure, the engineering and the optimization models that we have that might not be relevant in the future. if we don't take that societal change.
Thank you. Let's see, I don't see other questions right now. Are there any general questions for the panelists?
I can't see my raise your hand button, so I'm going to do it here on screen.
Go ahead.
Hi, it's Mike Patterson. I want to thank all of our speakers today and John and Mona for coordinating this special edition. On this last talk and through some of our earlier talks, the opportunities are being identified for where the community that U.S. CLIVAR works with, that there are avenues through which we can promote further engagement downstream. And I think this variations set of articles helps identify some of those initial targets so that we can co-convene discussion further downstream. I look forward to working with you and our members of our predictability, predictions, and applications interface panel that this work largely aligns with, so that we can follow up on some of the terrific ideas that have been put forward and keep the conversation going. So I wanted to thank everyone for their contributions and helping to contribute to our program's engagement at these interfaces. So thanks. Back to you, Mona.
Right. Well, unless there are any other questions, I think we'll adjourn. Thank you all so much for presenting this information. Thanks for being here. Thanks to Jenny and Mike for giving us the opportunity. For anyone who's watching this recording, we'll strongly encourage you to have a look at the special edition of Variations. This is the Winter 2022 edition. And we just heard a snapshot of very in-depth and thoughtful articles that our speakers and experts have compiled in that edition. So please have a look. John, any last words?
Nope, other than thank you and stay warm.
All right. Well, thank you again. Bye-bye.